Hi, and welcome. This is a quick demo of Federation Autoscaler, and here is its open source repository on GitHub. Meet Federation Autoscaler. 4 clusters, working together to move workloads where they're needed. On the left, the consumer, the cluster that needs more capacity. It runs the Cluster Autoscaler, a gRPC server, and the consumer agent. At the top, the central cluster hosts the broker, which makes every scaling decision. On the right, 3 providers stand ready to lend capacity. And here, a mock server feeds live carbon and location data into the system. First, we configure the providers. Each gets a price, a region, and a capacity limit. Provider 1 is the cheapest, Provider 2 the greenest, Provider 3 the nearest. Then on the consumer, we pick a policy and its region. These settings travel to the broker in the central cluster, which now sees every provider's cost, carbon, and location. We deploy 5 pods. 3 fit on the consumer, 2 overflow. With the price policy, the broker picks Provider 1, the cheapest. Liqo peers them, and the 2 pods run there. Delete the workload, and the resources are released. Now just change the policy to eco. Same workload, but this time, the 2 pods go to Provider 2, the greenest. Then we scale back down. Change it once more to latency, and the pods move to Provider 3, the nearest. Scale down, and we're back to the start. Same workload, 1 policy switch, cheapest, greenest, or nearest. That's Federation Autoscaler. Let's set everything up. We download the 1-command demo script from the repository, give it execution permission with shmod, and then run it, passing the IP addresses of our clusters. 1 central, 1 consumer, 3 providers, and 1 mock cluster that serves the carbon and location data. From here, Ansible takes over. It installs the tooling, then K3s, Cert Manager, Liqo, the broker, the agents, the gRPC server, and the cluster autoscaler on the related clusters, and finally verifies that the whole federation is healthy. In a few minutes, the environment is fully up. When it finishes, the script prints the dashboard links. First, the broker dashboard. The 3 providers are already advertising their capacity. On the consumer's Liqo dashboard, everything is empty. And the consumer console is blank too. Now the heart of the setup, configuring the 3 providers from their consoles. On Provider 1, we set the lowest CPU and memory prices, pick its region, and choose how much of its capacity to advertise with the sliders, then submit. This will be our cheapest provider. On Provider 2, we enter higher prices, but we give it the region with the lowest carbon intensity. This will be our greenest provider. And on Provider 3, we set its region to the location geographically closest to the consumer. This will be our nearest provider. For each one, the region drives 2 things behind the scenes: its carbon footprint, fetched from the eco mock, and its coordinates, fetched from the geomock. Every value we submit is saved to the provider's configuration and picked up on its next advertisement to the broker, about every 30 seconds. On the consumer console, we choose the placement policy. Let's start with price, and we set the consumer's own region, here London. We submit, and it's pushed to the broker on the next heartbeat. Back on the broker dashboard, all the settings have arrived. Now we apply the workload on the consumer, 5 replicas. 3 of them fit on the consumer's own node and start right away. The other 2 don't fit, so they stay pending. The Cluster Autoscaler asks the broker for capacity, and because the policy is price, the broker offers only the cheapest provider, Provider 1. Looking at the Liqo dashboard now, there's an active peering with Provider 1, and the 2 overflow pods are running on it. Now we delete the workload to trigger scale down. The pods disappear, so the borrowed virtual node is no longer needed. The Cluster Autoscaler asks to remove it. The broker releases the reservation, and the consumer agent tears everything down. It unpeers from Provider 1 and cleans up the Liqo resources. Now let's change only the policy from price to eco on the consumer console. Back on the broker dashboard, the target switches. With eco, the broker now prefers Provider 2, the greenest one. We apply the workload again, the same flow as before. 3 replicas run locally, 2 stay pending, and the cluster autoscaler asks for capacity. This time, because the policy is eco, the broker exposes the greenest provider, provider 2. A reservation is created. Liqo peers the consumer with provider 2. A virtual node appears, and the 2 pending pods schedule onto it. You can confirm it on the Liqo dashboard. Then we delete the workload again. The pods go away. The virtual node becomes unneeded, the reservation is released, and the peering with provider 2 is torn down, returning everything to the clean starting state. We repeat the policy change, this time from eco to latency, and submit on the consumer console. Checking the broker dashboard, the target moves again, with latency. The broker prefers provider 3, the cluster geographically closest to the consumer. And we apply the workload one last time. Just like before, 3 replicas run locally and 2 stay pending. Now, because the policy is latency, the broker offers the nearest provider, provider 3. The cluster's peer, a virtual node appears, and the 2 overflow pods run on provider 3, visible again on the Liqo dashboard. Finally, we delete the workload. The pods are removed, the virtual node is reclaimed, the reservation is released, and the consumer unpeers from provider 3. So with the very same workload, simply changing the policy, sent the borrowed capacity to a different provider each time, cheapest, greenest, then nearest. And that's the demo. With a single, unmodified cluster autoscaler, just one policy choice decided where our workload ran. Thanks for watching.